My name is Jim Al-Khalili. I'm a professional physicist, and I've been making films about my passionate interest in science for many years. I never cease to be astonished at the awesome power of science in shedding light on everything in the universe, from the tiniest things in existence to extraordinary objects on a cosmological scale. In this series, I want to show you how science gives us insights into the biggest questions of all. How did the universe come into being? How did life start on Earth? And how does it sustain itself? What is the nature of space and time, the very reality we live in? And how will it all end? In this episode, we'll look at the first two great pillars of modern physics: Einstein's general theory of relativity, which has radically transformed our understanding of space and time, and quantum mechanics, which reveals the mind-blowingly strange world of the subatomic. And we'll see how the quest to unite the two theories into a theory of everything has given rise to some extraordinary ideas about the fundamental nature of reality. I want to explore the latest developments and astonishing new theories that continue to shape the way we understand the universe. I hope this series will show you just how amazing our universe is. With a question. It may never have occurred to you to ask, but once you start looking into this question, the horizons it opens up are mind-boggling. Okay, so what is space? But does space only exist when there's stuff in it? Does space only have a meaning when it's enclosed by walls? Ultimately, the question is this: does space in itself have form? The properties of space were first described by the mathematician Euclid over 2,000 years ago in his legendary text, The Elements. In it, he laid down a set of simple logical rules about space in what today we call Euclidean geometry. For Euclid himself, and for almost all mathematicians for the next 2,000 years, these rules weren't just true mathematically. They were also true statements about physical reality itself. So they thought that two parallel lines would remain parallel forever, that a triangle in real space would always have angles adding up to 180 degrees. But, weird as though this might sound, it's not actually always true. Almost 250 years ago, in a small town in northern Germany, a mathematician was born. His name was Carl Friedrich Gauss. Gauss tackled many great problems in his career, but from a young age, he began to speculate that the rules of Euclid may not be as absolute as everyone had assumed. For example, on the surface of a sphere, the angles of a triangle can add up to more than 180 degrees. Let me explain with this globe. You see, we can see that it's three-dimensional because we can stand back and look at it. But what if you were an ant stuck on the surface? How would it know that that surface is curved? So imagine you're the ant and you start off at the North Pole, and facing south, you move down towards the equator. At the equator, you still face south and you shuffle sideways along the equator. Then you reach a certain point, and then you start walking backwards, so you're still facing in the same direction, and head back to the North Pole. Now, look what's happened here. You've been pointing south all the way round, and yet when you arrive back at your starting point, you're facing in a different direction. Understanding this gives us a way of calculating the curvature of a surface without ever leaving it.
This was an amazing insight, but it only applies to curved surfaces, which are two-dimensional. It would take a brilliant student of Gauss's, Bernhard Riemann, to develop these ideas in a way that could be applied to the three-dimensional space that surrounds us. Aged just 26, Riemann encapsulated his strange new ideas about geometry in a lecture that was to become legendary among mathematicians.
In June 1854, Riemann delivered his lectures to an enraptured audience. In them, he detailed how he'd taken Gauss's ideas on curved surfaces and generalized them, so that they applied not only to curved two-dimensional surfaces, but the curvature of space in any dimension. Okay, so I'm sure this all sounds rather complicated. What exactly do we mean by curved space in any dimension? So let me try and explain. Here's the thing, Gauss talked about curved two-dimensional surfaces. Well, here we have a sheet of paper, and it's two-dimensional. So if I curve it, we can visualize and see this curvature, but only because it's embedded in 3 dimensions. Now, what if we curved 3 dimensions? Presumably, we'd need a 4th dimension.
But how do you get to this 4-dimensional space? It's impossible to step outside of our 3-dimensional world. Wherever you travel in the universe, no matter how far you go, you're always stuck in 3 dimensions. The genius of Riemann was to show that you didn't need to stand in a 4th dimension to tell if space was curved. You could actually do it from the inside. But for Riemann, this would always remain a purely mathematical idea. It would take Albert Einstein to tie these mathematical ideas together and apply bendy, curved, non-Euclidean geometries to the real space that surrounds us.
In the general theory of relativity, Einstein took the mathematics of Gauss and Riemann and used it to paint a revolutionary picture of the physical world. He showed that, just as Gauss had suspected, the geometry of the space around us isn't always of the regular, flat Euclidean kind.
But if space is bent and warped all around us, surely we must be able to observe that this is the case. Well, we do, just not in the way you might expect. This was Einstein's major insight. He showed that it was the ability for space to bend and warp, for it to be flexible and change its geometry, that gives rise to the force we call gravity.
Now, since Newton's time, gravity was thought to be a force that pulls all objects together. So if I drop this apple, it's as though there's an invisible rubber band that's pulling it down towards the Earth. But Einstein's general theory of relativity gives us a completely different picture and a totally new perspective. So although gravity appears to be a force, it's nothing more than the curvature of space itself. When an object falls, it's not being pulled by gravity at all. It's just following the simplest path through bent space.
But the equations of general relativity didn't end there. They revealed that it was the presence of mass that caused space to curve and distort. The reason we have gravity on Earth is because the Earth is actually bending the space around it.
And although we don't perceive it like this, Einstein showed us that we live in a four-dimensional universe. The fourth dimension is time. The onward flow of time itself is also warped by gravity, just as much as the other three dimensions of space.
Gauss, Riemann and Einstein had between them come up with a description of how the space and time we exist in can be warped. They showed that space and time are not the fixed, unchanging stage on which the actions of the universe are played out. They're actually part of the performance.
Einstein's equations were also describing a universe that was expanding. Physicists found it hard to believe at first, but astronomical observations soon told them it was absolutely true.
But, and this is the crucial point here, it's not that the galaxies are flying away from each other through space, but rather that the fabric of space itself, in between the galaxies, is expanding. So the universe in its entirety is getting bigger.
And that led to an inescapable conclusion. If the fabric of space is expanding, then if you wind the clock far enough backwards, there must have been a moment of creation. The universe began with all of its energy squeezed into a singularity, a point of infinite density and gravity. From this earliest moment, space expanded rapidly, spreading matter and energy as it grew, to eventually create our vast universe. This event is known as the Big Bang. If you thought curving space and time is weird, you've heard nothing yet. Get ready for the impossible world of quantum mechanics.
To paraphrase one of the founders of quantum mechanics, everything we call real is made up of things that cannot be themselves regarded as real. And at stake, that everything we thought we knew about the world might turn out to be completely wrong.
We're going to start this journey into scientific madness by asking another fundamental question of physics. What is light? Well, you've probably heard of light waves, so perhaps you might imagine that light is a wave. Understandably, that's what many scientists thought too, in the age before quantum mechanics. It seemed perfectly reasonable.
All around us, we see light behaving in a perfectly common sense, wavy way. Look at the shadow of my hand. It's fuzzy around the edges. We understand this as the light hitting the sides of my hand and bending and smearing out slightly, just like water waves around an obstruction. Perfectly common sense, wave-like behavior. Rather like ripples on the surface of water, light was simply ripples of energy spreading through space. And this was as firmly accepted as the fact that the Earth was round.
But was this always true? Bit by bit, troubling evidence emerged that seemed to contradict the received opinion.
In the late 19th century, scientists were studying the then newly discovered radio waves and how they were transmitted. And to do that, they were building experimental rigs very similar to this one. Basically, by spinning this disk, they could generate huge voltages that caused sparks to jump across the gap between the two metal spheres. But in doing so, they discovered something very unexpected to do with light. They found that by shining a powerful light source on the spheres, they could make the sparks jump across more easily. This suggested a mysterious and unexplained connection between light and electricity. To understand what was happening, scientists used this. It's called a gold leaf electroscope. It's basically a more sensitive version of the spark gap apparatus. Now, first of all, I have to charge it up. What I'm doing is adding an excess of electrons that are pushing the two gold leaves apart. Now, first I take red light and shine it on the metal surface, and nothing happens. Even if I increase the brightness of the light, still the gold leaves aren't affected.
Now I'll try this special blue light, rich in ultraviolet.
Immediately, the gold leaves collapse.
Light can clearly remove static electric charge from the leaves. It can somehow knock out the electrons I added to them. But why is ultraviolet light so much better at doing this than red light? This new puzzle became known as the photoelectric effect. It was a big problem for physicists, and it may not surprise you to learn that once again it was Albert Einstein who provided the answer. This is the Achenhold-Sternwarte Observatory in Berlin. Perched on top is a strange, huge iron and steel construction. But it's not a gun. It's actually a telescope. Built in 1896, the telescope was one of the largest of its kind in the world and made the observatory the go-to place to engage and astound the public in new science.
Albert Einstein gave a very famous public lecture here on his theory of relativity, which is, of course, what he's most famous for. But it's not the work that won him the Nobel Prize.
In 1905, he'd also come up with a new theory to explain the photoelectric effect. And what he suggested was revolutionary and even heretical.
He argued that we have to forget all about the idea that light is a wave and think of it instead as a stream of tiny bullet-like particles. The term he used to describe a particle of light was a quantum. I'll try to explain how this helps using a rough analogy. Of course, like all analogies, it's far from perfect, but hopefully it'll give you a sense of the physics to help you understand why thinking of light as a stream of particles solves the mystery of the photoelectric effect. In this analogy, these red balls represent Einstein's light quanta.
And those cans over there are the electricity held in the metal.
Now, in the original experiment, they made electricity flow from the surface of the metal by shining light on it. In my analogy, I'm going to try and knock those tin cans over using these red balls.
Absolutely no effect. That's just like red light.
According to Einstein, each particle of red light carries very little energy because red light has a low frequency. So even a very bright red light with many red light particles can't dislodge any electrons from the metal plate, just like the red balls. Now I'm going to use heavier balls, like these blue golf balls, and I'm going to try and knock off the tin cans with these. They're like the ultraviolet light in the experiment. Now, each individual light particle carries more energy because ultraviolet light is higher frequency. Just a few of them, like a dim ultraviolet light, are enough to knock the electrons out of the metal plate and collapse the gold leaf. So Einstein's idea that light is made up of tiny particles or quanta is a wonderful explanation of the photoelectric effect. I remember when I first learnt about this, being blown away by its sheer elegance and simplicity.
Okay, so was Einstein right? Light is made up of tiny bullet-like particles? Well, yes and no. Fast forward past the First World War to the Roaring '20s, and another experiment which yet again bamboozled the world of physics. It's the birth of modernism, a time of cultural revolution and scientific revolution too. Most mind-boggling of all is an extraordinary experiment which challenged the very basis of reality itself. But weirdly, it was an experiment that wasn't even about light. It was about the particles that make electricity.
In the mid-1920s, an experiment was carried out at Bell Laboratories in New Jersey in America, which uncovered something entirely unexpected about electrons. Now, at the time, it was accepted without question that electrons were these tiny lumps of matter, small but solid particles like miniature billiard balls. In the experiment, they fired a beam of electrons at a crystal and watched how they scattered. Now, that's entirely equivalent to taking a beam of electrons, say, from an electron gun, and firing it at a screen with two slits in it, so that the electrons pass through the slits and hit another screen at the back. What the Bell scientists found shocked the physics world to the core. To understand why, consider a similar experiment with water waves. I've set up a simple experiment. I have a water ripple tank placed on top of an overhead projector. I have a generator producing waves that pass through two narrow gaps. The projector beams the image of the waves onto the back wall. You can see as the waves come in from the left and squeeze through the two gaps, they spread out on the other side and interfere with each other. What this means is that when you get the crest from one wave meeting the crest from another, they add up to make a higher wave. But when the crest from one meets a trough, they cancel out. This gives rise to these characteristic lines leading to the signature wave pattern. Bands of light and dark. Whenever you see these light and dark bands, the signature wave pattern, you know without doubt that you've got wave-like behavior. So, guess what they saw in New Jersey? Now it seemed that firing electrons, tiny solid particles, through the two gaps produced exactly the same kind of pattern, bands of light and dark. First, light, for a long time believed to be a wave, was found to sometimes behave like particles. And now electrons, for a long time believed to be particles, were behaving like waves. But it was actually stranger than that. The wave pattern wasn't merely some result of the entire beam of electrons. More recently, this experiment has been repeated in labs around the world by firing one electron at a time through the slits onto the screen. At first, each electron seems to land randomly on the screen. But gradually, a pattern forms. The signature wave pattern. Let me be quite clear about just how weird this is. Remember from the wave tank experiment where the signature wave pattern only exists because each wave passes through both slits and then its two pieces interfere with each other. But here, every individual electron, each single particle, is passing alone through the slits before it hits the screen. And yet, each single electron is still contributing to the signature wave pattern. Each electron has to be behaving like a wave.
One of the leading exponents of the new science of quantum mechanics was Niels Bohr. He and his colleagues built a new theory of light and matter, and they just decided to put up with how mind-bendingly strange it was.
As Niels Bohr himself said, anyone who isn't shocked by quantum theory hasn't understood it. So, viewers, I'm going to take our tiny electron and use it to delve deep into the heart of reality. And yes, prepare to be shocked, because this is the only way to explain what we observe when a single electron travels through the slits and hits the screen. Quantum mechanics says this: we can't describe what's traveling as a physical object. All we can talk about are the chances of where the electron might be. This wave of chance somehow travels through both slits, producing interference just like the water wave. Then, when it hits the screen, what was just the ghostly possibility of an electron mysteriously becomes real. Let me try and capture just how weird this is with an analogy. If I spin this coin, then all the time it's spinning, it's a blur. I can't tell if it's heads or tails. But if I stop it, I force it to decide, and it's heads. So before, it was sort of not heads or tails, but a mixture of both. But as soon as I've stopped it, I've forced it to make up its mind. This is what Bohr and his supporters claimed was happening with our electrons. In a sense, as it spins, the coin is both heads and tails. Similarly, the electron's wave of chance passes through both slits, two paths at the same time. Our coin then stops at heads. The ethereal wave of probability hits the screen and only then becomes a particle. The quantum world was unlike anything ever seen before. It's hard to overstate just how crazy this is. Bohr was effectively claiming that one can never know where the electron actually is at all until you measure it. And it's not just that you don't know where the electron is. It's weirdly as though the electron itself is everywhere at once. Bear in mind that electrons are among the commonest and most basic building blocks of reality. And yet, here's Bohr saying that only by looking do we actually conjure their position into existence. It's like there's a curtain between us and the quantum world, and behind it, there is no solid reality, just the potential for reality. Things only become real when we pull back the curtain and look. And this view, ladies and gentlemen, became known as the Copenhagen interpretation.
None of it seemed to make any sense. Yet it was proven true in experiment after experiment. So most scientists shrugged aside the philosophical problems and got on with harnessing the incredible power of this new science.
It simply didn't matter to them because it worked. They even coined a phrase for it: shut up and calculate.
Quantum mechanics led to a profound understanding of semiconductors, which helped create the modern electronic age. It produced lasers, revolutionizing communications, breathtaking new medical advances, and breakthroughs in nuclear power.
Still to this day, quantum mechanics remains a mystery we simply have to accept. It tells us that on the subatomic scale, there's no such thing as empty space, even in a vacuum. Particles are continually popping into existence and almost immediately cancelling themselves out. Space is seething with them, appearing and disappearing. And it's thrown up an even crazier sounding phenomenon which seems to defy some of the most sacred laws of physics. It's known as entanglement.
Now, entanglement is this special, incredibly close relationship between a pair of quantum particles whose fates are intertwined. For example, if they were created in the same event. Let me try and explain this by imagining the two particles are spinning coins.
Imagine these coins are two electrons, created from the same event and then moved apart from each other. Quantum mechanics says that because they're created together, they're entangled. And now many of their properties are forever linked, wherever they are.
Remember, the Copenhagen interpretation says that until you measure one of the coins, neither of them is heads or tails. In fact, heads and tails don't even exist. And here's where entanglement makes this weird situation even weirder.
When we stop the first coin and it becomes heads, because the coins are linked through entanglement, the second coin will simultaneously become tails.
And here's the crucial thing. I can't predict what the outcome of my measurement will be, only that they will always be opposite.
That was almost too crazy to imagine.
It's as if the two coins are secretly communicating instantaneously across space and time, even if the first coin was on Earth and the other was on Pluto.
Entanglement may drive the next technological revolution. It underpins quantum computers, machines that could solve problems which are far beyond the reach of the fastest machines that we build today. And yet it remains a mystery, because the laws of physics say that nothing can travel instantaneously across space. So how can these particles possibly be entangled with each other? It's something we still don't fully understand.
Ever since the two theories were developed around a century ago, scientists have suspected that quantum mechanics and Einstein's general theory of relativity were really just two sides of the same coin. Now, both theories describe our reality, but on very different scales. Quantum mechanics down at the subatomic and general relativity at the cosmic scale. So now the quest is underway to try and unify these two theories, to find a so-called theory of everything.
In recent years, an astonishing idea has been gaining ground with many theoretical physicists, which may possibly crack that problem. The idea came out of the study of those extraordinary objects in outer space, black holes. When a massive star collapses on itself, it gets smaller and smaller until it heads towards a singularity, a point of infinite density and infinite gravity. It's a weird structure composed of massively warped space and time. It's by studying black holes that physicists have been pursuing one of the biggest questions of all. What is space and time?
If you've watched my films before, you probably won't be surprised to see that I've decided to represent the awesome majesty and sheer destructive power of a black hole with a water slide and a rubber duck.
My poor little duck is about to fall into the black hole. And while it's not, of course, a literal analogy, if you can imagine the water in the slide represents space and time, I'm hoping my homemade contraption will at least give you an inkling of just how mysterious a black hole really is.
Now imagine that's the black hole over there, the swimming pool, and this is the unfortunate duck that's been caught by its immensely powerful gravitational field, and so will be pulled inexorably towards it. The big question is, what will happen to the duck as it approaches the black hole?
Now remember, Einstein realized that space and time aren't fixed or stable. They change according to your perspective and factors such as the speed you're traveling and the distortions of the gravity you're in. From the perspective of the duck, things will seem normal as it moves towards its inevitable extinction in the jaws of the black hole. At least that's what happens from its perspective.
But Einstein's general theory of relativity tells us that, from my perspective, something very strange indeed appears to happen.
So let's see exactly the same event again, but from my perspective. Because the duck is moving into stronger and stronger gravity, the space around it will distort more and more. The duck will mysteriously seem to get slower and slower and slower, from my perspective. Eventually, the duck will reach a point of no return. It's called the event horizon, and it's a place where gravity is now so strong that nothing, not even light, can escape. For me, it will seem as if the duck has frozen exactly at the horizon. General relativity says the duck will fall into the black hole, but I will never know, because it's impossible to see beyond the event horizon. And that's one reason why black holes are so mysterious.
Now, we can't be absolutely certain what would happen to the duck after it falls into the black hole, but it's a pretty safe bet that at some point the gravitational stresses inside the black hole are going to rip the duck apart. Now, let's take a different duck. In this case, a rather tasteful looking ceramic one. And I want to use it to demonstrate a very important idea in physics. But to do that, I'm going to need safety goggles and a hammer.
I'm sorry, but that felt rather good. But I think we can agree that you'd be very hard-pressed to put this duck back together again. But it's a very important principle in physics that, in theory, we should be able to reconstruct anything, even if it has been smashed to smithereens. So even if the duck has fallen into the black hole and been destroyed, the record of it, the information which could put it all back together again, should never be lost from our universe. But this leads us to a major paradox which is still unsolved. So we know that even if the duck falls into the black hole, the information that describes it can't be lost. But, and this was something discovered by Stephen Hawking, black holes have a temperature. They give off radiation, and if you leave them long enough, they'll just evaporate away. But now we have a really big problem. Where has the duck's information gone now?
All right.
Some of the world's leading theoretical physicists are wrestling with this very problem.
Hello. Hi, how are you?
Because it could have enormous consequences for our understanding of reality itself. Physicists such as Professor Sean Carroll.
If we want to talk about the black hole information puzzle at all, it's only a puzzle if you know the black holes evaporate. Because if black holes don't evaporate, then you can just say, the information's not gone, it's in the black hole. It's only when you say the black hole evaporates and it evaporates into featureless radiation that the information seems to be lost. So this is a puzzle. This is the real heart of the black hole information loss puzzle.
The paradox has led some physicists to an extraordinary suggestion. Although the duck falls into the black hole, what if its information somehow stays on the event horizon, in the same way as the duck seems to freeze to the outside observer? Professor Marika Taylor has spent years theorizing how this seemingly impossible concept might actually be true.
It turns out that the surface of a black hole really doesn't behave in the way that we would expect it from everyday life. So there are really strong quantum effects around a black hole horizon. And then as you throw something into a black hole, it might be absorbed in this complicated kind of quantum computer state. So you can kind of think here of something like in the Matrix movie, you know, some really complicated quantum physics going on. The information is kind of trapped there.
It seems that there is very, very good reason to believe that whatever information is inside the black hole can, in the appropriate senses, be thought of as living on the surface of the black hole.
To help us conceptualize this extraordinary idea, physicists refer us to a technology which exists right now. It's not an exact analogy, but it helps us understand the basic idea at the heart of it all. This new theory of reality is known as the holographic principle. The reason it's called the holographic principle is because a hologram generates a realistic-looking three-dimensional image, but all the information needed to describe the hologram is contained on a two-dimensional surface. Now, the next step in our story is quite extraordinary, because some physicists have extended the idea of a hologram to explain the entirety of our universe. So it could be that the holographic principle could describe the fundamental nature of everything.
So holography is the idea that the whole of our universe could really be understood in terms of something which lives in two dimensions. That's why people call it holography.
The idea is that somehow what you and I think of as the real, tangible, three-dimensional world is encoded on a two-dimensional surface. All the information there is located on that two-dimensional surface.
Professor Juan Maldacena is a world-leading physicist who's developed the idea of the holographic principle.
So the idea is that everything that is happening in our three-dimensional world is really encoded on the two-dimensional boundary, so some region very far away. It's like having a crystal ball, but the ball is very big at the edge of the universe. And yeah, so what's happening in the interior and what's happening in the boundary are two alternative descriptions of the same reality. And the physical laws, the fundamental physical laws on the boundary are simple, but they create a complex quantum state.
When Modestano first was giving talks in 97, 98, some of the reactions are, look, this has to be crazy, right? And it was only when he really started to flesh out the calculations, show how it worked mathematically, within 6 months or so, that the entire community was convinced by it.
After the initial skepticism, thousands of physicists around the world are now working on the holographic principle as a possible explanation for physical reality itself. This is a theory that could bring together the quantum world and the universe as described by general relativity into one all-encompassing theory of everything.
Now, it's important to say that no one has yet proved that we're all holograms. That's still theoretical speculation at the moment. But the mind-boggling concept, taken seriously by a lot of physicists, is that all the information needed to describe our three-dimensional space could be stored in a quantum state on a two-dimensional boundary at the edge of the universe. Now, that's quite something to get your head around.
We're still, in some sense, absorbing the paradigm shift, the philosophical consequences of this, because it is something very profound to say that really, the three-dimensional reality that we think we live in is deceptive, that when we get to the true quantum level, that actually there's a fundamental two-dimensional world. We need to understand this concept more. And we also need to see how we're going to see signals of this in our astrophysical data, in our cosmological data, in data that we get from particle colliders such as CERN. And I think by the end of this century, we'll look back at the beginning of the century and just be astonished about the way our perceptions of physical reality have actually changed.
Well, it's certainly not proven yet. But perhaps in 10 years' time, I'll make another film in which I tell you that, yes, it's been proven we are all holograms. Or maybe there's another mind-boggling theory, a whole new way of looking at reality that's waiting round the corner to be discovered.
In the next episode, we'll dig even deeper into the secrets of our existence. We'll see how some deceptively simple laws of physics explain how life can exist and thrive in the universe. We'll learn how the breathtaking complexity and exquisite patterns of nature can emerge spontaneously from simple mathematical rules. I'll investigate how the spooky world of quantum mechanics is now helping us understand some of the most important processes in life itself. And we'll ask one of the biggest questions of all: how did life begin?